Today we turn back to fundamental solutions for parabolic equations and establish some properties of those solutions. So I would like to recall.
Recording in progress.
We have given by some coefficients ij, s, x, e, aj, sx, bij, sx. They are given for I and j from 1 to d, and sx is from 0t or b. And we suppose that the following properties, the following conditions are fulfilled. The matrix B S X with the entries B I J is such that this quadratic form is satisfies the following inequalities. For all theta from RD and Sx Bij Sx minus Bij Ty is less than constant, some constant, t minus s to the power alpha over 2 plus x minus y to the power alpha. For all s, t, x, and y from this region, okay, where k and alpha some constants, positive constants, okay, and ij satisfies is ij of sx is a continuous bounded function on that region, and it satisfies the Hölder condition with respect to space variable. Okay, and we saw how to prove the existence of a function g s x t y given for s less than t, x from RD and y from RD, such that for fixed t and y as a function of s, of the arguments s and x, it satisfies the corresponding parabolic equation. I would like to write down it here. dg ds sx ty plus the sum over oj from 1 to d aj sx dg sx ty dxj plus 1/2 the sum over all I and j from 1 to d dij sx d2g sx ty dxj dxi equals 0 for all s less than t and x from Rd. T and y are fixed. Okay? And it is a continuous function in all its argument in this region, and it satisfies the following condition: integral over Rd gsx ty phi of y dy converges to phi of x as s goes to t for all x from Rd for any bounded continuous function phi on Rd. And now I am going to answer the following question. The following questions. The first one. Is it true or not that gsx ty takes on only non-negative values? The second, is it true or not that integral over all or d gsx ty dy equals identical to 1? As t, x, and y are such as it is written here. It is true or not that integral gsx tau z g tau z t y dz equals g s x t y. For all s less than tau less than t, all x from Rd and y from Rd. So if the answers on these questions is positive, then there exists a Markov process such that this function gsxty is its transition probability density. And we are going to show that this is the density of a diffusion. This is a diffusion. Process. With its drift given by the function vector valued function A as x and its diffusion matrix or operator given by the matrix valued or operator valued function B as x. We will use the maximum principle that was discussed in the previous lessons. Okay. So fix a function phi of x and put u as x given by the integral or Rd g s x ty phi of y dy. This function is defined for Sx in the domain here T cross Rd. I forgot to write down one more property of this function gsxty that was established on one of our previous lessons. G S X T Y satisfies the following estimation. Some constant t minus s to the power minus d over 2 x minus mu y norm y minus x square over t minus s for all s less than t, x from D and y from normal V with some constants K and mu. I would like to remember that we have the following representation for G. G is equal to G0 plus G1. G0 was given in an explicit formula, and G0 satisfies exactly this inequality. And G1 Sx Ty was estimated as follows: some constant K here and here may be different, but then for K from G0 and G1 may be different, but then we can choose common constant for both. Okay? T minus S to the power minus D over 2 plus alpha over 2. X minus mu y minus x square over T minus S. So if I T minus S to the power alpha over 2 replaced by T, I have the estimation of this type. So we have for G exactly this inequality. Okay? Now what I can say about the properties of this function. I see that it is a continuous function with respect to Sx for fixed t. For fixed t. Okay, it is a continuous function, and it satisfies the following inequality. Constant, that constant. Norm phi is supremum over all z, absolute value of phi of z. Okay, and that integral can be written as follows: E exp minus mu z square dz. So this function is a continuous bounded function. Okay?
And what about t minus s to the power?
I change variable here.
Okay.
Y minus x over x square root t minus.
So this is just a constant.
Yes. This USX is a continuous bounded function. Okay? And it satisfies, according to this property. It satisfies the Kolmogorov backward equation. U prime Sx plus 1/2 trace dsx u second prime x sx equals 0 for all sx 0t ugly. Okay, so we can apply the theorem from the previous lesson, according to which if we have a continuous function in this region such that it satisfies this equation and it allows to be estimated in the following way: minus b x beta x square in this region. Then if this function is non-negative on the right hand of this interval, then it is non-negative at any point of this type. Okay? We proved such a theorem. If we have a continuous function that satisfies if this operator is LU, if it satisfies LUSX is non-positive, okay, and it satisfies the inequality of this type, then if it takes on only non-negative value at for s being equal to t, then it is non-negative for all sx from this region. Okay? But I know that if phi USX was defined by the following integral phi of y GSX ty dy. If the function phi is a continuous and bounded and it takes on only non-negative values, so we have this condition of our function. Okay, so we can apply the theorem mentioned above, and we can assert that this is non-negative for all Sx if phi of x is non-negative for all x. Okay? So we have that this integral is a non-negative function, a continuous function with non-negative values. And this property implies that the function gsxty takes only non-negative values. Why? If for some sxty, gsxty takes on strictly negative value, then I fix sxt and consider it as a function of y. It is a continuous function. So there exists a ball of radius delta with the center at the point y, such that this function is negative for all z from this ball. Then there exists a continuous function phi of z such that its support contains in this ball, and that function is non-negative. And if I consider this integral for such a phi, I cannot obtain here a non-negative value. Yes, this integral for such a function is strictly negative, and it contradicts to our properties. So the function gsxty takes only non-negative values. So the first property is established. Okay. Now consider, let us define the function phi 0 of y that is equal identically to 1. Okay, if I consider such a function integral over Rd g s x t z phi 0 z dz, this function satisfies this equation. Okay, we have to integrate this equation with respect to this parameter y. Okay, this equation, and it satisfies the initial condition. This goes to 1 if S goes to T. But you see, phi 0 of y satisfies this equation and this initial condition. Initial in the sense of final. Okay? And we know that the solution to this equation, that was the second theorem from the previous lesson, the bounded solution to this equation is if there is a bounded solution to such equation, then there is only one. So this solution coincides with this. It is identically equal to 1. So we established the second property. Okay. Let us prove the property C. So we have 3 instants of time fix some function phi of x that is continuous and bounded. And we know that the function g s x t y phi of y dy this function as a function of sx is a solution to the Cauchy problem. L U equals LUSX equals 0 for SX from 0 to T cross RD. And the final value is phi of x for x from RD. Okay? And now I consider on the interval 0 tau cross RD, I consider the following function: integral over RD GSX tau Z U, denote this function by USX, okay? U tau Z dz. Okay? This is the solution to the following Cauchy problem. L, denote this function by U1SX. L U1 equals 0 for SX 0 tau RD. And U1 tau minus X equals U tau X. So on the interval from 0 to tau, I have two solutions to such a Cauchy problem. Two solutions. One of them is given by this integral, and the second one is given by this integral. And what I know about those solutions, I know that they are bounded. For example, absolute value of USX is some K, maybe K1 norm phi. Okay, so the same concerns this function U1. It is also bounded. Okay, so I have two bounded solutions to this Cauchy problem. But we know that there is only one solution satisfying the following, that only one solution satisfying allowing the following estimation. It is evident that if the function is bounded, it satisfies this, it can be estimated by this expression. If we put beta any, we can put beta any positive number, okay? So there is only one solution, and we can write down that this integral integral coincides with the integral gsx tau z u tau z dz coincides for all s x from the interval 0 tau cross Rd. Okay, and now this the expression on the right hand side of this equality can be written as follows: integral over Rd integral over Rd. This function is given by g tau z t y phi of y dy. Okay, and I should integrate it with respect to this measure gsx tau z dz. And if I change here the order of integration, I obtain the following. Integral over Rd phi of y integral over Rd g s x tau z g tau z t y dz dy. So you see this integral coincides with this one for any bounded continuous function phi. And it means that this function must coincide with this one for almost all y. But this function is continuous in y and this one is continuous in y. So we have exactly this equality that is satisfied by the fundamental solution we have constructed. Okay.
Nikolai Ivanovich,
Yeah.
is it possible to give the following proof? Consider left hand side of C and take u of phi of z g tau z tau y.
Okay. Yes.
So this is a convolution, so it satisfies L of u is 0. And we know that the right hand side also.
Okay.
So is it possible to do like this?
Yes, I think so. Okay. And now it remains to verify that this transition probability density, we can say that it is a transition probability density because it is non-negative and the full mass is equal to 1, and it satisfies the Kolmogorov-Chapman equation. So we have transition probability density. Okay, and is it true that its local characteristics coincide with given functions a as x and b as x? Let us make a little break. Continue. So
Recording in progress.
we have to verify that the diffusion coefficients for the Markov process with this transition probability density coincide with given function a as x and b as x. So let us consider the following integral. Oh, I would like to make one remark before I start. We, on one of our previous lessons, we saw how to solve non-homogeneous Cauchy problem. LUSX equals minus F S X U T minus X equals phi of x. If fsx equals 0, we know that the solution is given by this integral over rd phi of y g s x t y dy, and we saw that the solution to this problem with phi being equal to 0 is given by the following integral over the interval from s to t d tau integral over rd g s x tau z f tau z dz. We establish this formula for the solution for a solution to this Cauchy problem in the case when a as x was equal to 0 and b as x was equal to identity operator. Okay? But it is not difficult to understand that this formula is valid in the general case. So this is the solution for a homogeneous equation and non-homogeneous initial value, okay? And this formula gives the solution to non-homogeneous equation with homogeneous initial value. And it can be written, this formula can be written, and it will be satisfy this equation under the following condition on this function. It must be locally, this formula is valid for the function f satisfying the following condition for any z there exists some delta such that for any y from the ball of radius delta with its center at the point z, there exists delta and some constants beta and k such that this difference in absolute value is estimated by k z minus y to the power beta, where beta is positive, k is positive, okay? The function f must satisfy the Hölder condition locally uniformly with respect to tau. Okay? Then this function can be differentiated with respect to x twice, and it satisfies exactly what this equation. And if it is not fast increasing on the infinity, so this the final value for this function as s goes to t must be 0. Okay, so this sum gives the solution to this non-homogeneous Cauchy problem. Okay, and now I write down here this integral as the sum gsx ty y dy minus Okay, this is vector value function. Let us multiply it by theta in order to deal with real valued functions. Okay, so here we have theta.
We have y twice near dy.
Oh, thank you. Thank you. I'm sorry. X. Okay. And now I know that this function, it is not bounded, okay? But that integral exists, and it can be estimated as in the following way. This integral is less than theta constant absolute value of x. Maybe plus 1. So this function satisfies the homogeneous, this function satisfies the homogeneous if it is u1 of s. If it is denoted by u1 as x, then L u1 as x equals 0. And u1 t minus x equals x theta. Okay? And what about this function? This function satisfies the non-homogeneous equation L if it is denoted by u2 as x. So L u2 as x equals a minus a s x theta. Okay, and u2 of t minus x equals minus x theta. Okay, so the sum, the difference between u1 and u2 is a solution to this equation with phi being equal to 0. Okay, and f being equal to a as x theta. According to this formula, I can write down this sum as the integral over s, or the interval st d tau integral over rd a tau z theta g s x tau z dz. A tau z satisfies the Helder condition with respect to this argument z. So this is the solution to this equation with 0 with phi being equal to 0 and f being equal to minus as, not minus, f being equal to as x theta. And now if I divided this by t minus s and s and t, so as a consequence of this equality we have the following property. Limit as t goes to s, 1 over t minus s, integral over rd, y minus x theta, g s x tau z, dz goes to a, not goes, is equal to a s x theta. Okay, but this is the second condition in the definition of a diffusion. The first one was we have to estimate the following norm to the power 4 gsxt y dy. This is not a definition but a sufficient condition for the function to be.
Excuse me? Don't we have to write s goes to t? Because I think the integral does not depend on t, and we will get
Oh yes,
division
yes.
by 0. So s must go to t.
No, here
Okay.
here was written t. Thank you. Okay, but we have the estimation k integral over rd y minus x to the power 4 t minus s to the power g over 2 x minus mu y minus x square over t minus s dy, and it is not difficult to see that if this is a constant t minus s square. So the first condition was as follows: integral over rd y minus x to the power 2 plus delta g s x t y dy must be converge as t minus s goes to 0 to 0. So we have for delta being equal to 2, that condition is fulfilled. Okay, and now it remains to verify that the diffusion matrix for this function gsxty is inside this B. consider the following function: y minus x theta square g s x dy dy. Integral over rd y theta square g s x dy dy plus x theta square minus minus 2 x theta integral y theta was has been just calculated. It is equal x theta plus integral over s over the interval from s to t d tau integral over rd a tau z theta g s x tau z dz. So we have here again the sum of two functions, integral over rd y theta square g s x dy dy minus x theta square. This is the one. And the second one is minus 2x theta integral over the interval st integral rd a tau z theta g s x tau z dz. Okay, let us consider this function. You see that estimation of this function allow us to write down, consider here of unbounded function, but not that that are not increasing very fast on the infinity. Okay? So this function satisfies the equation. Let us denote it by V1. L V1 equals 0 and V1 of t minus x equals x theta square. Okay? And if, I'm sorry, V1 is only this function, okay? And this is V2. Okay, so V2 satisfies the following equation: L equals V2 is with its sign. Okay, so minus 2x theta a s x theta, and minus 2 not 2 b s x theta theta, because 1/2 we have the coefficient 1/2 b before b. Okay, so the sum of that function the sum v1 plus v2, okay, v1 plus v2 L satisfies this equation, and 0 v1 plus v2 t minus x equals 0. Therefore, by this formula, we can write down that sum as follows. Integral, or maybe v1 sx plus v2 sx is equal to integral from s to tau, the tau integral over rd y theta a tau z tau y theta g s x tau y dy plus integral the tau integral over rd b tau y theta theta g s x tau y dy. Okay, this is representation for these two terms in this equality. So we can write down the following equality. This integral equals to the sum integral over the integral b tau y theta G S X tau y dy plus we have this minus this, okay, plus 2 integral y minus x theta a tau y theta g s x tau y dy. You see, we have very nice formula. Now if I divide this by t minus s, y minus x theta square g s x t y dy, and if t minus s goes to 0, then I obtain here ds x theta, and this item goes to 0 because you see we have the following estimation for that integral. Two norm A norm theta square integral over the interval the tau integral norm y minus x g s x tau y dy, and our estimation for the function g allow us to estimate this integral as some constant t minus s to the power 1/2 tau minus s to the power 1/2, and if I integrate it, I obtain t minus s to the power 3/2. So divided by t minus s, it goes to 0. Okay, so the function that we constructed gsx ty is indeed a transition probability density of a diffusion process with its coefficient being given beforehand. Okay, ASX and BSX. Okay, that's all for today. See you next Tuesday. Thank you.